أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين حمدا يوافي نعمه ويكافئ مزيدا يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك اللهم صل على محمد وعلى آل محمد اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا اللهم
اللهم
اجعلني في
اجعلني في
قلبي
قلبي
نورا
نورا
وفي
وفي
لساني
لساني
نورا
نورا
وفي
وفي
بصري
بصري
نورا
نورا
وفي
وفي
سمعي
سمعي
نورا
نورا
وعن
وعن
يميني
يميني
نورا
نورا
وعن
وعن
يساري نورا
يساري نورا
ومن
ومن
فوقي
فوقي
نورا
نورا
ومن
ومن
تحتي
تحتي
نورا
نورا
ومن
ومن
أمامي نورا
أمامي نورا
ومن
ومن
خلفي
خلفي
نورا
نورا
واجعلني في
واجعلني في
نفسي نورا
نفسي نورا
رب اشرح لي
اشرح
صدري
لي
ويسر
صدري
لي
ويسر
أمري
لي
واحلل عقدة
واحلل
من لساني
عقدة من
يفقه
لساني
قولي
يفقهوا قولي.
اللهم افتح علينا حكمتك وانشر علينا من خزائن رحمتك يا أرحم الراحمين سبحان ربك
آمين
رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
آمين آمين يا رب العالمين. Thank you to Mr. Akasha. We are now going to start our class. As you see from the agenda, we will finish up our topic 6, part 4, the last part. Then the other half of the class, hopefully the other half. Then we will enter to the new chapter, which is topic 7, which is very interesting, of course, definitely. So without further ado, I will share my slide. Hold on a second. And while waiting, maybe you can start up downloading topic 7 lecture notes, which are already available in class materials under topic 7. Okay, so I hope you could already see my slide. I'm going to scroll down to part 4. Right. All right, so as you can see, this is the last slide that we did on the part 3. If I scroll further back, I have given you the additional notes which are which is in the separate file on the simple mechanisms on writing the change of concentration. And we did the first equation, the irreversible equation, then reversible equation. The remaining examples are not shown in class, but I hope you could read this on your own. And if you still have questions in writing the proper equations for respective concentration equation, if you still have that problem, then you could message me personally, yeah, until the last equation, yeah, with the parallel equation of A producing B, then A also producing C. So now we are going to enter the last part of topic 6. It's still about the multiple reaction, but then we have an additional name for it, which is complex reaction. Mainly because we are going to deal with many simultaneous equations which need to be solved simultaneously, and in order to do that, we can use ODE solvers. For example, polymath itself, which is the ordinary differential equation. There are a few steps that you can follow here as written on the slide, starting with of course, I'm going to go back. The mole balance, writing the net rate of reaction, writing the rate loss, writing the relative rate of reactions, and finally stoichiometry. They are all not new. They are all very basic, which you have covered since the beginning of this semester. And what is important that you have to practice writing the relative rate of equations. Yeah. In this case, because we are going to deal with multiple reactions, so the relative comparison of the rate of reactions against other species, not only from the same equation, but also from the other equation. Yeah. So just imagine that if you have 10 simultaneous equations, then you have to practice writing the relative rate of reactions. Yeah, of course. Let us go to the next slide, showing you on the flow chart, not to say the flow chart, but charts on guidance in using the ODE solvers. Yeah. Of course, we are dealing with complex reactions. Let's say they are parallel or series. And if we are dealing with liquid system or gas system, so therefore we can apply the writing the mole balance equation by writing the concentration formula or the molar flow rate. So you need all those equations in order for you to solve the complex reaction, yeah, by using solvers. Even though we have these ODE solvers which are going to calculate all the respective parameters automatically for you in in condition that you have all the complete parameters fed into the programming. Yeah. The next slide shows you two tables showing the multiple reactions with the example of different configuration. Yeah, starting with the batch PFR, then we have PBR. The B here means bad. The P is packed, bad, and R is the reactor. Yeah, so we don't really cover much on the PBR, but at PFR, yes. If I'm not mistaken, the PBR going to be covered maybe, yeah, in the reaction engineering too, if I'm not mistaken. Other than that, of course, as usual, the common CSCR and one example of a batch reactor, but since we have two streams coming in, the pure A at one stream and the slowly added B, yeah, the different stream, then we call it semi-batch B added to A. So we're going to cover these formulas one by one in the next coming slides. Yeah, this is just to show you the summary. Now, let us start by writing the mole balance. Okay. We will start with batch reactor. You know that for batch reactor, you can write the equation based on the concentration. Of course, those equations come from the mole balance equation. Yeah, knowing that you don't have the flow in and flow out. So finally, you may write the change of moles per unit time. Yeah, in batch is equivalent to the rate of formation of the species times the volume itself. So let's say if we have two species, then you can write those two species with two different equations. Let's say if we have more than two species, then you can further on writing other equation for each of the species. If it's 100, then please write 100 times, yeah, something like that. Now, the same thing, you can re-express the number of mole by the concentration, yeah? And the same thing, repeat that for as many species involved, yeah, for that particular reactor, in this case, batch reactor. Now, we're going to go to the next one. So this is PFR. Of course, using the same mole balance, having the inlet and outlet present, then writing the molar and concentration equation for PFR is simply, this one should already be at your fingertips, yeah? The change of the flow for that particular species. If you have the other species, then write the same thing over the change of volume. Because you know we have change of volume along the length of the PFR, which is equivalent to its rate of formation for that particular species, and simply re-express the F, which is equivalent to the concentration times the volumetric flow rate. So it ends up with that equation, yeah, the expression of the change of concentration over the length of the PFR by the change of volume, which is equivalent to the rate of formation divided by the initial flow rate. Yeah. Sorry, symbol tak betul. I'm going to erase that. Upsilon. Okay, pen. Epsilon not initial. Now, do you have any question before I proceed? Nada? Afsar? Azra? Okay? Afifah? Okay. Nazrin dari tadi yang go je. Okay, bagus. Mashita? Okay, So, I'm going to go to the next slide. Chapika. Now. Hi, Shafika. Are you okay? Dah makan? Saya sebelum kelas makan 2 pinggan nasi. Sekarang rasa macam nak tidur dah. But I already book myself before the class. Lepas kelas, I nak solat dan nak tidur. Macam mana tu? Akan macam gelak ya. So we're going to go to CSCR. As usual, the same mole balance equation. In this time, of course, you consider your F coming in and F coming out. Then you write the volume for the CSCR based on the change of the molar flow rate divides by the exit rate of reaction, assuming that the rate of reaction inside the CSCR is equivalent to what you collect at the outlet of the CSCR. So the same thing, writing the volume simply by re-expressing the F by that equation, so you get an expression for V in the function of concentration. Very easy. So we're going to go to the last one, which is, this is simply the batch reactor. It is called semi-batch, simply because you have the one stream feeding in pure A initially and later on slowly adding the B at a different stream. So we call it semi-batch. So the change of number of moles of the A, simply the normal equation that you have for the batch, then the number of moles of the B over the change of the number of moles of the species B, which is here, over the time is simply the initial B inlet or fed into the semi-batch plus the rate of formation times the volume. Yeah, because no, that's right. Yeah, it depends on the initial and the whatever is existing before. Yeah, of course, when we are relating to B, then it has to be B there. Same thing goes to here, simply the re-expression of the number of moles to concentration. All right, so we're going to go to the second step, which is writing the net rate of formation of each species. Okay, so what do you mean by net rate of formation of each species? Net rate of formation. So it's easy. Rate of formation is the positive R for each species, and considering all the number of reactions, yeah? Net means what? So we're going to have a look at that. Let us first start taking the examples of 4 equations. Equation number 1, equation number 2. When I say equation, means equation for the reaction number 1, yeah? So reaction number 2, reaction number 3, and reaction, simply put a name there. So we just chose Q, yeah, reaction Q. Let me ask you, out of the 4 reaction equation, how many species do we have there? Nazrin, how many species do we have there?
7.
Bagus, 7. Seronok jawab betul. Betul lah tu. Dana betul ke? So what are those 7?
A, B, C, D, E, F, G.
Kalau 10 alfabet apa Nazrin? 10.
J.
Betul je ya. Akasha dah keluar jari dah. Kalau I kata 30 agaknya dengan jari kaki semua okay. Alright, very good. So now The next slide will show you how do we write the net rate of formation. Yeah, we already know that we have spasm pula. Nak sebut seven dengan species jadi spasm. 7 species. Yeah, we're going to go to the next slide. Ini seronok sebab saya di angkasa. Rasa macam di awang-awangan. So, let's start with the steps that we can do in writing the net rate of formation here. This one. We will start by writing the reaction and the rate constant. Of course, you have written the reaction. We have 4 kinds of reaction. Then we will write the rate constant. So we know that this is reaction number 1. So the rate constant number 1 for species A. All right. Then it says there our assumption with respect to the limiting reactant for the rate constant. So the red bold red alphabet are considered to be the limiting reactant, as you know from the elementary equation, and of course the number of stoichiometric value. Then this is A, okay, A, B, of course either one, so A is normally there. A plus 2C, then A, 2B, 3E, then B, E plus 2F, then E. Yeah, so the red bold alphabets are the limiting reactant. So we're going to write the rate constant based with respect to the limiting reactant and also number of equation or reaction. Which reaction? This one is reaction number 2. So the rate constant for reaction number 2 with respect to the limiting reactant A, K, reaction number 3 with respect to the limiting reactant B, and finally KQ with respect to the limiting reactant E. Okay, we're going to go to the next one. Writing, this is done, that is done. The third one is writing the net rates of formation. So simply adding all the rates of formation for all species, yeah, for every reactions. Let's say we choose to write the rate of formation for all species, but only for only for all reactions, but only for species A and B. Yeah, this is just an example. Yeah, we just choose to practice writing the net rates of formation for only 2 reaction. Yeah, in reaction number, only for 2 species A and B, but for all number of reactions. Yeah, let us start with the first one, species A. So in just if we have 4 reactions, so simply R1A, R2A, R3A, RQA. Same goes to B. Yeah. So we are using this formula, rate of formation J species is simply the summation, yeah, of all the species of all the number of reactions, not species. Q here is number of reactions for all the rate of formation for all species there. Yeah. Okay. So let us start with the first one, first example that we wrote for species A, but we're going to check whether they are present or not. For example, in equation reaction number 1, do we have A? Yes, we do. So we write the rate of formation of A. Do we have, in reaction number 2, do we have A? Yes, we do. Thank you. So we have R2A. In reaction equation number 3, do we have A species? No. Thank you, Karina. Dah geleng situ. So we cancel that out. In equation Q, do we have A? Apa benda ni saya bulatkan ni? Salah ni. Do we have A? No, we don't. Nada, Nazrin, Shafika, thank you. We don't. So we are going to cancel that out. Yeah. Okay. So let's check with the species B. Yeah. In equation reaction 1, do we have B? Yes, we do. Amani, Nazrin, thank you. Adriana, yes. Reaction 2, do you have B? No, we don't, Afifa, so cancel that out. Reaction number 3, do we have B? Yes, yes, yes. Sengih-sengih ya. The last equation, do we have B? Oh, Daniel, dari tadi kurang je. Aku lah sikit. Okay, so that you will see the summary of this example later on, but we're going to go to the third step, yeah, writing the rate loss. Okay, now how do we write the rate loss? It's very easy, yeah. Reaction number 1, if we have A as the limiting reactant, so we simply write the rate of disappearance of the A. So this is assume I forgot to mention this. I'm going to go back to my previous slide here. The assumption that we're going to make is the elementary equations. Yeah. So let's say this is an elementary equation. So it's much easier for us to write the rate loss equation. Yeah. K1A for reaction number 1, species A, simply CA times CB because you have 1 stoichiometric value. Then for reaction number 2, K2A, then CA and CC to the power of 2 because we have 2 stoichiometric value. Same goes to 3, blah, 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 E, blah, blah, blah. Tak ada sebut blah, 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 blah je. Okay. The last equation, KQE, CE, then we have 2, then CF squared. Right? Very easy. Next. Now, this is where we substitute the rate loss equation to the net rate of formation. Yeah, this is where we have deducted the other unwanted or unpresent rate of formation for that species A. So simply substitute the rate loss equation to that equation, yeah, later on. Now, same goes to here, R3B. And what about R1B? Yeah? Here we wrote R1A. So the same thing, the rate of disappearance of species B following the same format. Yeah? K1B, CA, CB. Yeah? All right. So normally when you write those formulas in ODE solvers, you don't really have to substitute those each equation in that net rates of formation. Yeah, you simply add in the formulas and the computer will detect it itself. Yeah. All right. Now the next step would be writing the relative rate of reaction. This is the most interesting part, yeah, which you have seen earlier from the earlier topic. So we're gonna have a look at this again, and they are very useful for you to make a relationship between the rate of formation, or in this case we have negative rate of disappearance of the reactant to the rate of formation of the product. Yeah, when we have that relationship, so how do we easily tell the solvers that you can use these formulas to solve your unknowns? Yeah. So before we do that, there are two kinds of reactions here, of course. Single reactions and multiple reaction. They are both the same, except that for single reaction, you don't have the I here. I here means I equals to 1 is reaction equation number 1. I equals to 2 is reaction equation number 2, blah, 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 until certain number of yeah, n there. Yeah, but both are explaining the same thing. And the only thing is here for one single reaction, here for multiple reaction. Multiple reaction. All right, so we're going to go to the relationship. So what do we need to do? Yeah, we're going to input all the possible equation for the ODE so that the ODE can use them as solving the multiple unknowns. Yeah. For multiple reactions, we want to relate the rate of formation of each species to one another. All right. Now, let's say you see here, This is the reaction number 1, I equals to 1. I'm going to go back to our previous, this one. This is equation number 1. So the I is equals to 1. So this is what we're going to do now. I equals to 1. Writing the relative rates of equation. The two ratios are referring to the reactants. Then the next two ratios are referring to the rate of formation. Now what we want to do is to relate species A to species B. Okay, so simply using that relationship, species A is equivalent to the species B, whatever that we write there. So this is what you see since the A and B are all both 1, So you see there over 1. So write the rate law, Then from here, since coincidentally CA and CB are the same, then we can assume K1A is actually equivalent to K1B. So therefore, the rate of formation of species A in reaction number 1, I equals to 1, is equivalent to the rate of formation of species B in equation reaction number 1. And both are the same as minus K1ACACB, since K1A is equivalent to K1B. So you could also write minus K1BCACB, right? Okay. Bagusnya, seronoknya Anggo. Let's go to the next slide. Now, we are going to make a relationship between the A to C. All right. Here, we have done earlier, A, I'm going to use different color. We have done earlier A to B. That is done. Now we are going to correlate or make a relationship of A to C now. So how do we do that? We got here A to C. So simply write that relationship. All right. The A to C. Okay. So R1C is equivalent to the final equation. How do we get that? Of course, simply solve that relationship, Minus 3 R1A, and we know R1A is such and such equation, then simplify it. All right, very good. Next slide. We have done A to C. Now we're going to correlate or compare between A to D. Okay, the A to D. So this is what you see. The A to D, then R1D is equivalent to R1A, the same thing, right? Next, this is now the equation number 2. Equation number 2, the one that you see earlier, equation number 2, A plus 2C. A plus 2C, okay? We are again going to write the A to C. Have we, A to C. Okay, here, A to C. And later on, A to E. So this one, A to E. It's just that on my slide, the arrangement starts with A to E. Yeah. So what is R to E? Yeah, simply simplify that equation. Yeah. Simply simplify that equation. Okay. Which is K minus R to A. Substitute the R to A. Yeah. Then we got minus and minus, now it becomes positive. All right, now we're going to go to the second one, the A to C. Yeah? A to C. A to C. Yeah, simply solve that equation. So what is R to C, which is equivalent to 2 R to A? So we know that earlier R to A was obtained from, mana dia? R to A. R to A. R2A. Mana R2A saya? R2A. Here. So R2A. Tapi kita buat dengan kenapa pula tiba-tiba saya blank letih kot petang kot. Takkanlah tak reti tulis R2A. Inilah. Ya Allah. Tiba-tiba dia jadi blank pula. Agaknya kena tukar background ni. Sekejap nah. Akan terlebih banyak ni. Sekejap nah. Jangan terkejut. Hold on. Barulah seronok sikit. Okay. Now. Where was I? Okay. R2A, which of course that is the R2A equation. Yeah. Simply simplify that by the R2C. I hope you don't have any question, right? Do you have any question? Umairah, tak ada. Hana ni, tak ada. Alia tak ada. Ashikin, tak ada. Nurin tak ada. Mashitah, Adriana, Syafiq, Amani, tak ada. Ashikin, yang Fazlika, tak ada. Afifah, tak ada. Okay, we're gonna go to the next one. Jangan pening-pening. This is just a summary of all the species. A, B, C, D, E. This is how you learn to write the net rate of formation for each of the species. And we have made the correlation from our previous slides. So simply write down everything. I'm not going to repeat all of them, but you could see that we got ranges of rate of formation, yeah? Net rate of formation or rate of formation for the 1A, 2A, 1B, 1C. Yeah, okay, of course, this is the lain sebenarnya 1C sini. 2C, 1D, 2E. Okay, 1A, 1B, 1C, 1D, 1E, 2A, 2, where is my 2B, 2, where is my 2B, 2C, apalah Mizun. Itulah kata kelas petang dia jadi pensyarah pun jadi blur. Ada ke duk cari 2B? Cuba bagi jawapan kenapa tak ada 2B? Cik, cover line. Marah student pula.
Tak ada dalam reaction dia. Tak ada dalam reaction.
Awak ni memalukan saya je lah, Kasha. Buat jawablah tak tahu. Barulah saya sedar hati sikit, semua orang tak tahu. Ada letih kot. Ada ke nak cari 2B faham? Tak ada pun. Ya Allah. Thank you Akasha. Okay, let's proceed. Okay, the last part is writing the stoichiometry. Now, this is the thing that you always write. For example, if you want to write the concentration equation, the molar flow rate, and of course, we got two kinds of ways of writing the concentration. One is for the gas phase and the other one is the liquid phase. Liquid phase is very straightforward, dealing with the molar flow rate and the initial volumetric flow rate. Then gas phase, we have the ratio of pressure and temperature. So if the system is isothermal, the temperature is the same, then you simply cross that out, which the ratio becomes 1, same goes to isobaric. Yeah. Now, I'm going to go to the multiple reactions in PFR. This slide is only summarizing the equations. Of course, we start with the mole balance. This is the common equation that we use for PFR. Then the relative rates, rate loss, the net rate of formation, then the stoichiometry. Yeah, the same thing. The only difference is that, of course, not difference. Dekat sini pun sepatutnya ada the total concentration, yeah, initial. It's the same thing based on the ideal gas law. All right. Now, so this is the interesting part. I'm going to take a longer time doing this. Can we just take our 5 minutes break? Yeah, because if I give you a break in between, then dia punya cerita tersekat-sekat. Because this is a long way to go until step number 7, so it may take like 10 minutes, yeah? So we're gonna take our first 5 minutes break ke? Dan saya nak minum air saya. Yeah? Alright, thank you. Yeah. Apa? Cari air anggur. Edited dengan teh ke apa? Nak teh je. Okay, Assalamualaikum warahmatullahi wabarakatuh. I am back. I hope you are also back at your seats. So, berjaya dapat mission minum air. Oh, Nazrin bijak. Tak apa yang besar sebelah. Saya tak bijak lah tadi. Oh, Ashika pun bijak. Ya, saya ambil saya punya botol air, okey? Okey. Mari kita sama-sama minum air. Tengok siapa punya botol air yang hebat. Hebat tak? Botol air saya ada awan. Magic. So let's proceed, yeah? I hope everyone's there. Azri, are you there? Amani, Adriana, Shafiq, Madan, Azian. Ready, yeah? We're gonna put a lot of focus here. Fazlin, Amira, thank you. Iman, Kairia, Azri. Okay, we're gonna put a lot of focus here because it's quite intensive focus, yeah? In writing the multiple reactions for PFR. The example that we're gonna use here is only 3 reaction equation. Reaction number 1, number 2, number 3. Then you have the equation of the reaction itself, 1, 2, 3 respectively. Then on the right hand side, we have the rate of reactions, yeah? Now, before I go to the next slide, we noticed that, but first I'm gonna ask you how many species do we have here? Mr. Shafiq? How many species?
Five.
Okay, Shafiq says 5. Iman?
5.
5. Azri?
6.
Azri 6. Shafiqah?
6.
6. Nazrin?
6.
Nazrin dah tanya dah tadi. So supposedly 5 or 6?
6.
6, yes. We have ammonia. We have nitrogen oxide, 1, 2. Nitrogen, 3. Water, 4. Nitrogen oxide is done already. Nitrogen is done already. Oxygen, 5. Nitrogen, oxygen done. And nitrogen dioxide. Mr. Shafiq, yeah? Okay, now, we got 3 rate of equation. And the rate of equations are written based on the key reactant. Now, what does it mean by the key reactant? Yeah, we are dealing with multiple reactions. Let's look at the equation reaction number 1. We have ammonia, we have nitrogen oxide as the two reactants. So first, of course, the first equation, we will start with the rate of disappearance of the reactant. But here, which reactant that we are going to consider? Now we are going to write based on the key reactant. We got two candidates, ammonia and nitrogen oxide. You remember earlier when we write the rate of disappearance, we normally choose based on the rate of disappearance of the limiting reactant, correct? Now, my question would be for equation reaction number 1, what would be the possible limiting reactant?
Ammonia.
Ammonia. So Mr. Akasha says ammonia. So why don't we write the rate of disappearance of ammonia? Why? The
Because
answer,
it's not the key reactant.
because
It's not the key reactant.
why is it not being the key reactant? Yeah, the answer would be, why do we call it key reactants? Remember, we are dealing with multiple reactions, meaning the first reaction may be related to the second reaction. If you notice from the second reaction, in the reactant, we also have nitrogen oxide. Yeah, meaning whatever that we have nitrogen oxide here will also be used in the second reaction. So it's going to be the key reactant, which is relatively related to the next reaction. Yeah. So what is important is we want to see the rate of disappearance of the nitrogen oxide from the first reaction, which you also use that in the second reactions. For the second one, what would be the key reactant? Okay, remember, try to relate reaction number 2 to reaction number 3.
It's a nitrogen.
Nitrogen, yes, it's nitrogen. It's nitrogen, yeah? So we are going to write the rate of formation in reaction number 2 with respect to nitrogen. Then in reaction number 3, the nitrogen reacts with the oxygen, producing the nitrogen dioxide. So that will be your end product. And for the last reaction equation, we again write the rate of disappearance of the oxygen, yeah, because we already have the nitrogen there. So we are not going to repeat the nitrogen here. We are going to write what is not yet written, which is the oxygen there. All right? Okay. Now, so let us go to the inputs that we are going to give to the ODE solvers. There are 7 things that we should write, yeah, 1 till 7, which starts with first writing the mole balance equation, second writing the rate law equation, third to relate all species for each reaction to one key component. Fourth, write the net rate of reaction for all species. Fifth, write the equation for the unknowns. Yeah, it could be concentration, it could be the rate constant. 6, write the molar flow rate. Since we have many species, then total molar flow rate. Yeah. Then lastly, input all known parameters with values of initial concentration, for example, rate constant, and so on. Yeah. So having all and this slide shows you the summary, yeah? For example, we're going to go to each one by one, yeah? But I'm just going to say it here. the total equations that you will be writing is 31 equation, yeah, based on the guidance from step number 1 till 7, add them up. So in total, for the 3 simple multiple reactions, you will need to input in ODE solvers with 31 equations, yeah? So let us start one by one. Step number 1, by writing the mole balance equation, we know that we have 6 species and we are dealing with PFR. So it's simply the change of molar flow rate to the volume for all the species. Nitrogen oxide, ammonia, nitrogen, oxygen, water, and nitrogen dioxide. All of them on the right-hand side, which are equivalent to the rate of formation for that particular species. All right, so that is step number 1. Step number 2, writing the rate law equation. Of course, you have written all that already. Yeah, number 1, number 2, number 3. Step number 3, here step number 3, we got 3 sub-steps, 3A, 3B, and 3C. So 3A, relate all species for each reaction to one key component. So how are we going to do that? Simply by using the relative rate of equation formula. What do we need to do? We are going to relate it to the key component. Let's say 3A is referring to reaction number 1, this one. The key component is nitrogen oxide. So this is nitrogen oxide, yeah? Not yes, not no. So NO, nitrogen oxide. All right. So we are going to relate ammonia to nitrogen oxide. Sorry here. Nitrogen to nitrogen oxide, water to nitrogen oxide. Yeah. Use the relative rate of equation. So you have this resulted equation. The rate of formation of ammonia, nitrogen, water to the nitrogen oxide. Simply use the relative rate of equation, yeah? Step number 3B, same thing, but here for reaction number 2, this one. All right, so we are going to write the other species to the key component. What is the key component? Nitrogen. So use the relative rate of reaction equation, the relative rate of equation, compare it to the other species. Yeah, in this case, the NO to nitrogen and oxygen to nitrogen. Next one, reaction number 3, 3C, reaction number 3. Okay, the key component is oxygen. So nitrogen to oxygen, nitrogen dioxide to oxygen. Nitrogen to oxygen, nitrogen dioxide to oxygen. Right? Simply use the relative rate of equation. Step number 4. Now we're going to write the net rate of reaction for all species. For all species, right? Simply the summation of all rate of formation of all species in all reaction equation. So this is the one that we have practiced earlier. The nitrogen exists in reaction number 1, yes. Reaction number 2, yes. Reaction number 3, no. Correct. Ammonia, 1, yes. 2, no. 3, no. Nitrogen, 1, yes. Yeah, 1 here. Then 2, yes. 3, yes. Okay. Oxygen, only the 2 and also the 3. Okay. Water, only at 1. And nitrogen dioxide only at the last reaction equation. All right. 5th step. Now we have written the net rate of formation, the R, all the R. Then we have written the rate loss. We have written, all the rate of reaction equation. Yeah. What we have not written is, let's say, the concentration. We don't know the concentration. So we want to write the formula for the concentration, yeah? Equation for unknown like concentration. This is what you know, all the species, the nitrogen oxide, the nitrogen, the ammonia, the oxygen. Right, equation four unknowns of the C equation. Why? Because we have this ammonia, this nitrogen oxide, oxygen, and nitrogen. All right. We only write the unknowns equation from the rate loss equation. Yeah. Simply following the PFR concept, which is the molar flow rate times the total concentration initial over the total molar flow rate. Okay, so the molar flow rate here over the total, molar flow rate of the species over the total, molar flow rate of the species over the total, molar flow rate of the species over the total. Okay, here we don't have the correlation of the P's, correlation of the T's, yeah, we don't have that with the assumption that it is isobaric and isothermal. Remember, we are still in the chapters of assuming that the reaction of reaction condition is having a constant temperature. Later in topic 7, you will start to learn the common find the common scenarios that you will have in the industry, whereby the temperature is not always isothermal. Yeah, it is non-isothermal, meaning during the reaction the temperature changes. So therefore, if you have that, of course you cannot make that assumption as one, that ratio as one. Yeah, for this case it is still valid because that is the assumption that you make so far. All right. Step number 6 is writing the total molar flow rate, simply adding all the species, 7 species, the molar flow rate, yeah, giving you the total molar flow rate. And step number 7, write or key in the unknowns of all the K's. Where do we get the K's here? From the rate law. Yeah. So we need that value. So how do we get those value? Remember, in our previous chapters, previous one at the beginning of the semester, we look into the example of determining the specific rate constant. Yeah. If you don't have it, then you may try that in the lab, or maybe some people may have investigated it and simply refer to the published value, yeah, for the specific rate constant. Yeah. Okay. Now, for CSER, we follow the same principle. In this case, when there is no volume change, we can use concentration as variable. Yeah, meaning simply write the rate of disappearance of the limiting reactant A times V. Simply follow that formula, yeah? The final flow rate minus the initial flow rate. If there is volume change, use molar flow rate. So how do we do that? So this is the example of equations that we can write for the change of the molar flow rate, yeah, which is equivalent to the minus R1 times V, right? Simply the summation of all the rate of disappearance of all the species. This case not species, yeah, for all the number of reactions to the final number of reaction equation, yeah. So that will be the end of part 4 for topic 6. Okay. Okay. So are you ready for the next topic? Do you have any questions so far before I go to topic 7?
No, doctor.
Okay, thank you, Nordada. Nornada. So can you please have a look at your topic 7 PDF? Please check whether it's okay or not because I am going to share my topic 7. Oh, belum buka. Hold on. Okay. So we are now in topic 7. Topic 7 is very special. Now we can no longer we can no longer write the same equation for not all, but we have some additional equations that we have to consider because we are dealing with non-isothermal condition. Yeah, we are still going to use the same textbook and Alhamdulillah, for topic 7, I start to use the 5th edition already, yeah. I don't think we will still refer to Lebenspiel, yeah. We'll see, maybe in the future, I don't know. But I have prepared part 1 and part 2 ready for you. And there are at least another one part which I need to give you an extra, yeah. But later on, I will share that with you. Now, we are in non-isothermal condition and we will consider adiabatic and non-adiabatic. And of course, the main assumption is still steady state. And the example of reactors are PFR and CS here. So what is adiabatic? Oh, ini masalah saya tak selesai lagi ni. Sekejap dah. Dia berjalan dengan sendirinya. Hold on. So mind me, I'm not going to slideshow, yeah, for these few slides. I don't know what I could figure out. But anyway, so kalau you on tu macam, alamak, ada hantu ke apa? Dia tak buat apa-apa pun. But it's not, yeah, it's not. I don't know. I think saya buat animation kot, tapi I just couldn't find it. I checked it this morning, memang tak ada. Oh, lupa pula. Alright. Now, for non-isothermal, simply when during the reaction, the temperature changes. It is not constant. So when temperature changes, the energy also changes during the reaction. So what is important is when we are dealing with isothermal condition, we write thermal balance. Now, for the non-isothermal condition, we write the energy balance. So when we want to write the energy balance, we have to know how to write the equation for a system. So let us start writing the energy balance for a closed system. Yeah. Here we have heat flow, heat based on heat, flow to the system minus the work done by the system. Yeah, if the system receives heat, then work can be done. Yeah, and the results of that heat flow to the system minus work done to the surrounding is equivalent to the change in total energy of the system. So the symbol that you see here is what we call circumflex, yeah? So E circumflex refers to the change in total energy of the system. Now, what about if we have open system, yeah? Open system means you have a system, but there are flows coming in, yeah? So we have flow in, we have flow out to the system. So we can also write the energy balance based on the continuous flow reactors, for example, representing open system. Again, for that system, we have rate, heat flow. Yeah, it's a heat flow. Then we have W, the work done. And that W is very special. We have work of the shaft. What is shaft? So you have impeller, and that impeller needs to revolve or rotate. Yeah. So how does it rotate automatically? It is connected to a shaft, and that shaft is connected to a motor. Yeah. And that motor is connected to the electricity. With the electricity, it will drive the motor to rotate the shaft, and automatically the impeller will rotate. Due to that, the rate flow of the work for the shaft. So it's a well mixed open system, yeah, because we have this impeller thing. We have flow in, flow out. We have Q in, then we have work flow from the shaft. And due to the change of temperature, we have enthalpy. So that is enthalpy. H refers to enthalpy. All right. So we're going to go to the next slide. The energy balance for the continuous flow reactors, simply the rate of accumulation of energy within the system is equivalent to the rate of flow of heat to the system, which is a Q dot. Then the rate of work done to the system on the surrounding, which is the work. Yeah, the work. And of course, work, we have two kinds of work, shaft work or the rate of flow of work, the rate of flow of work, which is equivalent to the molar flow rate times the volume, mole per liter, mole, yeah, yeah. Jap, nak padam jap. Tak boleh padam. Sabar. Tak boleh padam. Padam. So this is flow rate and this is P, yeah, pressure, and that is volume. That is rate of flow work. Then we have another work, which is work of the shaft. Plus the rate of energy added to the system by flow into the system, right? Flow in times energy in minus the rate of energy leaving the system by the mass flow out. Mass flow out, molar flow rate out times the energy out. All of the terms must be homogeneously with the same unit, which is joule per second for both left and right, right? Now, we got energy balance also written when we make an assumption of unsteady state. Yeah, kalau dia unsteady state, how do we write the equation? Yeah, but of course later, if we assume steady state, that we can cancel out the total energy or the rate of energy change over the time which is equivalent to Q, 0. And the right hand side is simply the one that you see earlier, the rate of flow of heat to the system from the surrounding, Q dot, minus the work plus the summation of the rate of energy added. Yeah. Here in this case, we have EF, the same thing you have here, FE, yeah, it's the same thing. But inlet, then outlet, right? Then take note, we have I here, generally to refer to the type of species. Now, what you can see here is that we have Q, rate of flow of Q to the system. Then we have a flow work entering the system, which is the rate of energy added by mass flow into the system. Then rate of energy added by mass flow out of the system. Then the rate of energy can also be defined as the internal energy U, or kinetic energy, or potential energy, or other energy into the system. So if you write the rate of energy, it's simply the internal plus the kinetic energy plus the potential energy and others. Yeah. Then we have the rate of energy added, including internal kinetic, potential, and other energy out of the system. One coming in, one coming out. The same thing to the rate of energy by the mass flow, yeah, which is the flow work. Flow work entering and flow work exiting. Now, we are still writing the energy balance for an open system. We still use the same assumption, unsteady state, and in a almost chemical reactor, kinetic, potential, and energy are considered negligible. About sini, we got kinetic, we have, potential, internal, kinetic, and potential. Now it says that in writing the energy balance, we can assume that the kinetic, potential, and other energy into we have kinetic, we have internal, are considered to be negligible. So we are not going to consider that for both, entering and also leaving. But we are considering the mass flow into, which is the workflow, and the workflow coming out from the system. Now, the third assumption is that enthalpy or heat transfer and work teams are not negligible. The thing that you say negligible is the kinetic, potential, and other energy in a chemical reactor. But we cannot assume enthalpy to be negligible. We cannot assume heat transfer to be negligible. We cannot assume work to be negligible. So therefore, it ends up with this correlation. The molar flow rate times the enthalpy, which is equivalent to the molar flow rate times the, in parentheses, the internal energy, the pressure, and also the specific molar volume. Okay. Now, banyak equation ni. So, kelas tadi saya dah habis, tak adalah sampai sini. Tapi kelas petang semangat pula kan, laju. I think I'm gonna stop here because the more I go, and it might be very difficult for you to absorb, because it needs to be absorbed slowly, Why not you first read that lecture notes dulu, then you will need to listen to it when we have in the next lesson, So the remaining time, can I use that remaining time for you to make discussion among your group mates? Hari tu kan kamu disuruh buat video kan? Dah buat ke belum? Dah buat Dah submit belum saya? Dah submit?
Belum submit lagi, baru buat.
Oh, baru buat. Dah siap belum?
Dah siap.
Oh, dah siap.
Dah submit.
So why not you, I'm just going to make it an open activity. I'm not going to open breakout room, sebab kalau saya buat breakout room, automatically then it will randomly put you into the breakout room. I don't know whether you want it or not, but you can have your own activity. Or maybe you want to have your activity with your friends dalam breakout room. Macam mana? Atau nak buat own activity? Hari ni saya pantas lah pula. I don't plan it to be that fast supaya, because energy balance ni quite heavy, quite heavy. So give me a suggestion. What do you want to do for the remaining time? Katakan for the next 50 minutes.
Own activity.
Own activity. Macam mana nak buat own activity tu?
Try fahamkan balik.
Bincang dengan kawan, try fahamkan, nadamkan balik.
Okey, kalau you nak bincang dengan kawan, you nak bincang kat mana?
Saya bincang kat sebelah.
Apa yang cakap tu? Apa yang cakap? You bincang kat sebelah dengan siapa?
Saya bincang dengan Azri.
Mana? Mana tengok-tengok? Mana Azri? Izwan dengan Azri duduk satu rumah ke? Azri, datang kejap. Sekejap, I nak tengok possibility breakout room ni apa benda. Choose people loh, choose people. Dia kalau Cisco tu kita boleh buat breakout room je, then you boleh join je, you nak masuk mana kan. Ini team saya tak boleh buat. We'll assign people rooms for you. How do you want to assign people? Choose the people you want in each room. Okay. So you may have your own activity. Then I don't know how you're going to do that. Give me cara you nak buat sekejap. I tahu apa nak buat, I nak buat. Let me see. Okay, cuba you tengok. Can you have a look at your main teams? Dekat bawah general tu belah kiri, nampak tak channel number 1? Nampak tak? Number 1, nampak tak channel number 1 sebelah bawah
Nampak.
general? Nampak?
Nampak.
Nampak.
Okay, sekejap ya. Set channel moderation preference, channel moderation. Everyone can start a new post. Everyone except guest. Okay. Please try pergi kat situ. You boleh buat apa? You boleh masuk tak? Dekat channel number 1. You boleh masuk tak? Oh, boleh masuk? Okay. So, I'm gonna create ikut channel. Hari tu ada berapa group? Hari tu berapa group? 6 5? Okay. 5. I'm gonna create 5 groups. Okay, you may choose whichever group, arrange it with your classmate, yang group hari tu, if you want to have further discussion. So you choose your group 1, 2, 3, 4, 5, yeah? So if you want to make further discussion, just enter that room. Boleh? Sendiri-sendiri, boleh tak? Alright, so we have 5 rooms, right? I'm going to create another one, 6 room. I think hari tu 5. Alright, just add another one. So arrange it with your friends. Kat mana group mana, you group mana yang hari tu yang sepatutnya you ada discussion. Yeah, for the video making. Okay, so I'm going to leave you till 5:50 in your own room. All right? Ya.
Please. Kita buat tadi lot.